Hold a strict forearm plank for 60 full seconds, and you will feel an immediate, intense structural stress. The muscles of your anterior core tighten and strain to maintain a rigid line against gravity. Despite that intense physical exertion, your body is burning surprisingly few calories. The static nature of the hold keeps systemic energy expenditure remarkably low. Yet clinical protocols for obesity and weight loss routinely prescribe core stability exercises, like the plank, to drive body recomposition. To resolve this apparent contradiction, we have to decouple muscle activation from metabolic energy expenditure. High tension does not equal high caloric burn. We can see the mechanism of isometric body recomposition by mapping the mechanical anatomy of tension, and then dissecting the specific cellular pathways that tension triggers. A plank is a third-class lever system. The axis sits at the hips, resistance at the forearms, and core muscles generate upward force. The anterior core dominates, generating over 87% of the activation to prevent collapse, while the posterior chain acts as a secondary stabilizer. The specific amount of muscle activation required in this lever system scales directly with the angle of the body relative to the floor. Moving from a straight arm to a forearm plank decreases the elevation angle. This flatter alignment pushes the center of mass further from the support base, increasing internal downward torque. To maintain equilibrium, the core must drastically increase its maximum voluntary isometric contraction. The intense physical effort in a low plank is a mathematical response to mechanical disadvantage, not an indicator of calories burning. Fitness tools can intentionally manipulate this mechanical disadvantage to artificially raise or lower the percentage of MIVC required to hold the position. A Cielo Journal clinical study tested this by measuring front plank EMG activation while subjects used a TRX suspension system at 4 different heights. This chart displays abdominal group results. Dropping the TRX height to 10 centimeters creates an extreme spike in electromyographic activity compared to 85 centimeters. Table 1 reveals that at 10 centimeters, the maximized distance forces the rectus abdominis to fire at 134.8% of its maximum voluntary contraction. We can apply the inverse of this manipulation to purposefully reduce mechanical torque, protecting injured joints in clinical populations. The text here details the mechanics of an ergonomic foam block called the jack block. Resting the chest on this block physically shortens the distance from the support base to the bending point at the hips, creating a much more stable bridge. This table outlines the result of that shortened lever arm. EMG activity plummets down to just 4.1% for the anterior deltoid and 5.3% for the rectus abdominis. By understanding static equilibrium and lever mechanics, physical therapists can precisely engineer the exact isometric load on a patient's core based entirely on their current baseline strength. Moving from macroscopic lever arms down to the microscopic level reveals the biological reality inside the muscle tissue during these static holds. Continuous neuromuscular tension physically clamps down on the local vascular system. The rigid muscle fibers crush the network of blood vessels woven between them. This restriction of blood flow traps blood within the muscle tissue, rapidly depleting local oxygen reserves. Without a steady supply of oxygen, the body is forced to switch to anaerobic energy pathways. This triggers a massive, localized accumulation of lactate and severe metabolic stress. Compare that highly localized, oxygen-starved environment to the physiological requirements of dynamic calisthenics like burpees or jump squats. Dynamic movements continuously pump blood through the body. They spike the heart rate and drive massive systemic oxygen demand, which is the actual biological driver of high caloric expenditure and fat oxidation. The searing burn of a 1-minute plank is the signal of local anaerobic fatigue and lactate accumulation. It is not an indicator of systemic calorie burn. If a plank only generates localized anaerobic stress and burns minimal calories, we have to look at why clinical trials repeatedly demonstrate its effectiveness for obese patients seeking weight loss. A 12-week trial published in the Allied Medical Research Journal tracked a group of patients with a BMI over 30 who engaged entirely in a supervised core stability program. This chart tracks the results. After 3 months, the patients achieved clinically significant reductions across all major physical metrics, ending with an average BMI of 27.53, a body fat percentage of 30.14, and a waist-to-hip ratio of 0.85. The primary driver here is that intense isometric training successfully preserves and even builds lean muscle mass while a patient is in a caloric deficit. Maintaining that dense, lean tissue raises the body's resting energy expenditure. The patient burns a higher baseline of calories throughout the day, even while completely at rest. Furthermore, enduring that extreme local metabolic stress forces the core to develop strict neuromuscular stability. This creates the structural efficiency required to safely handle heavy dynamic movements later in their training. The isometric plank is a structural foundation, not a cardiovascular fat loss tool. Mastering static tension builds the biomechanical armor necessary to safely execute the high-impact dynamic exercises that actually oxidize fat and drive long